Alright guys, sorry about that. For some reason, I could not click everything the way I was supposed to. Um, Seems to be working fine now, but sorry for the couple minute delay in that. So we are going to start today talking about special right triangles. Just make sure you can, say hi in the chat so I can kind of just see who I'm kind of talking to. If you have questions, just jot them down in the chat, or if not, I'm going to keep going. We're going to start today with special rights. And hola, we've got bilingual. I find that the special rights that we're going to start with, isosceles right triangles, are a lot easier to start with, just because you don't really need the trick that we're going to look at. A lot of things that you're going to find in math, there are so many multiple ways to do them, and I know I just got done with my Honors Algebra 2 class, and that's something that we talk about all the time. You don't need this to solve the problem, but it's a faster way to do it. So a lot of these are just kind of shortcuts, and this is one of those situations where you guys will see that. Now I know we also talked, when we talked about congruent triangles, that you could solve it by side angle side, but maybe angle side angles faster. Or especially for instance, angle side angle, you could solve a triangle or say that it's congruent to another triangle, but angle side was there faster. So we always have these little shortcuts, and that's kind of what we're looking at today. So the first thing that I want us to look at is just what an isosceles right triangle actually is made up of. So when we look at a triangle that is isosceles and right at the same time, we obviously have the right angle. We know that the only two sides that could possibly be congruent have to be the legs, because the hypotenuse is supposed to be the longest side. And what ends up happening is this idea that you have your 90-degree angle here, and our two complements that are out here end up becoming 45 degrees. So a lot of times what you'll see is, instead of them calling it isosceles right, or right isosceles is typically the way it should be said, you'll see them called 45, 45, 90. And if you have my formula sheet that I kind of gave you, and it still says OGT at the top from years ago, one of the formulas on that formula sheet is at the bottom, and it actually is titled 45, 45, 90. So don't be surprised if that's how you see it referred to. And it's just this idea that if you see the two 45s, you're supposed to know that the two sides are the same, and vice versa. So it does, if sides then angles, or if angles then sides. So with that being said, we're going to cut to the chase already. We're going to talk about questions that could get asked. And for example, you are simply going to get asked, you're simply going to get asked, find the length of the missing sides. And there's no tricks. You absolutely can use the Pythagorean theorem. There is no reason why we can't choose to do that. So if I was to do this problem using the Pythagorean theorem like we've always grown accustomed to, we know that if this side is 12, and we do know that if the angles then the sides we are fully aware this guy's got to be 12. So AB, you are already able to answer doing 0 work whatsoever. However, I can find AC by doing the Pythagorean theorem. So we end up with 12 squared plus 12 squared equals AC squared. And we end up with 288 equals AC squared. And again, I am certain you are fully aware that there is 0 opportunities for decimals. So hopefully it does help, though, that it does have the 144s up here. And so 2 times 144 would have been 288. So that means when I take the square root of both sides, 12 radical 2 is going to be our length for AC. So I actually took all of these examples today off your next no reassignment. So for the 9 of us that are here today, 8 of you right away will know that I am going to, I think, answer 1, 2, 3, 4, 5, 6, 7 of your no re questions, which should probably leave maybe only about 7 more for you to complete on your own. And if you do recall, a lot of those are always duplicates. So yeah, I did the no reassignment last night just to make sure I wasn't, I could cut to the chase. I know, Audrey, you had emailed me a question. I did not get to it till late, but I did send that back to you. And I did post it for everyone online at Google Classroom as well. So in case we were all wondering, and you can thank her for that, because that was a really good question, especially if we didn't recognize that that's how that was being folded over. So make sure when you get to your no re question, you are going to be asked, there's going to be a blank for AB. You're just going to plug in 12. There's going to be a blank for AC, and you would have to access that radical in the drop down, and those are going to be the 2 answers. And that's it. So what I want to discuss with you now is the reason that I said there's a shortcut. I want you to think about this. What if I gave us another example? This time, so obviously, we're going to look at the exact same picture. I'll move this up now. And X, Y, Z. And I told you this side was 5. And I'm going to ask the same question. We're going to find the length of the missing sides. Well, I want you to think about this now. You're going to still be able to do the Pythagorean theorem. You're going to still end up with this repeated pattern like you see here with the 144s, but instead isn't going to be 5 squared plus 5 squared. So you're going to end up with 25 plus 25. You're going to end up with 50, and you're going to be right back here to 5 radical 2. So what do we talk about in our, with these shortcuts? All right isosceles triangles, and it has to be that it's right isosceles. It's not going to be any other type of triangle. Have a consistent ratio for the sides. And that is, so it's almost like the formula appears around the triangle. So again, it has to be isosceles, has to be right, and you will find that it is A, and always, whatever that value is, radical 2. Always. So it doesn't matter what the side lengths are. If it's 12 or 5, you automatically know that the other one has to be the same, and that the hypotenuse will always be that value radical 2, and you can see why it's going to happen. You're always going to have that repetitive leg that creates that situation. So when we talk about shortcuts, if you see this ratio, 1a, 1a, a times radical 2, that ratio is considered a 1 to 1 to radical 2 ratio. 1 times a, 1 times a, radical 2 times a. So I don't actually have to do any work here if I already see this pattern. So in this case, instead of going through all this stuff up here like we did with the Pythagorean theorem, I could just say that zy was 5 and xz was 5 radical 2, and I'm done. And again, it's just a shortcut. So you can do the Pythagorean theorem, or you can use the shortcut. So let's take a look at another example, because that's all this is. We're done. All the tricks, all the notes are done. Now it's just recognizing your patterns. And I do know that one of the things that's going to cause probably some questions is the minute we get a radical involved. So we're going to find the missing side lengths. And I'm giving you a question that I said is right off of NORI, so maybe you'll get lucky and get the same question. So again, the radical is what we get a little bit touchy with. So you have your option. You could do the Pythagorean theorem, or you could work with the special rights. So I'm going to do this both ways. I'm going to look at our Pythagorean theorem. And we could have radical 7 squared plus radical 7 squared equals MP squared, which we know here that anytime you have a square and a square root, they're going to cancel. So we're going to end up with 7 plus 7 equals MP squared, or 14 equals MP squared. When we take the square root, we end up with the square root of 14 is MP. Now, we know that we can't simplify this because 2 times 7, well, 2 is a prime number, 7 is a prime number, it's not going to work. So the length of MP is radical 14, and we already used that the length of NP is radical 7. And we're done. So you have your Pythagorean theorem. Now you could do this by using your special right formula for 45, 45, 90. And again, that is recognizing that if we have all of these, and I do suggest, at least this is me, setting this up using a different color so that I can see that my formula is separate. So A radical 2 across from the right angle on our hypotenuse. And I can already see that right here I have a value and the formula. So I have a formula on that side, and it already is named a value. So they're on the same side. They're the same segment. They're the same length. They're equal. So what I just found out is everywhere I know my formula for A is, I'm going to plug in radical 7. So that means here is radical 7. And over here, I'm going to plug in radical 7 for A, but it's still times that radical 2 that's sitting there. Well, radical 7 times radical 2 is that radical 14 that we already found doing the Pythagorean theorem. So again, when I would go to list this answer, I would know that NP was radical 7 and MP would be radical 14. And that's the nice thing about our special rights that are specifically right triangles that are isosceles. We don't have to worry about which one do we have to use. It's either or. It doesn't matter. Whatever you're most comfortable with. I will tell you, in the long run, that guy's going to be faster. All right, so let's take a look at another one. Again, right off of your no reassignment. Now, I'm not going to, again, tell you which way to do. I am, however, going to stress that the special rights are going to eventually be faster. So I'm going to do this one just with special rights. So I know the legs are both A and A. The hypotenuse is A radical 2. And thankfully here, I already have what A is. So we know A is going to be 3 radical 5, which means this side is 3 radical 5. And over here, I'm going to plug in 3 radical 5 for A, but I still have that radical 2. So I know that my missing sides are 3 radical 5 and 3 radical 10, because 5 times 2 is 10. And you're done. Another one. Find the length of the legs of a right isosceles triangle if the hypotenuse is 11 radical 2. All right. So this question, all in words, and I do suggest drawing it out. So what I'm going to do is all of the above. I'm going to draw this out. It says that it's right isosceles, so right away I put all my tick marks in. And it does say that the hypotenuse is 11 radical 2. Now, what I do know is that the unknown sides are going to be the same. So I can put them as x and x. Now, many of you might already know what the answer is, and that's fine, but I am going to show you the reason for this pattern, because I'm going to do the Pythagorean theorem again. And a lot of times we just kind of forget that we have these options and we jump to the first thing that we think about, and that's perfectly fine. That very well could be the most efficient way at that point. But what we know is that I could do the Pythagorean theorem, x squared plus x squared equals 11 radical 2. Now be careful, all of it gets squared, not just the square root. So you got to be careful, especially plugging things into your calculator. I have 2 x squares added together there. So 2x squared equals, and what I want to keep in mind here is that I have to square the 11 and I have to square the radical 2. Okay, those are those things we bring back from Algebra 1. And what we end up with is 121 times 2. So 2x squared equals 242. We're going to divide away our 2. And we're right back to x squared equals 121. So you just found out that the legs are 11. The reason why our special right pattern is such a good thing to remember is if I was to do this and I had my special right pattern, A radical 2, it's already in the pattern. And again, on this side, we already have our value and the formula. So if they're on the same side, they're the same length, they're going to be equal to each other. So A radical 2 equals 11 radical 2. Well, if we want to solve for A, we're going to divide away a radical 2. It's going to cancel on both sides. Now, you can visually see that, but if you need to be reminded why it mathematically happens, so right away, you already know that both sides are 11. So again, visually, you can tell me that the legs are 11, and you're done. No worries, Scarlett. I see that. You'll be able to catch up, and you can pause me if I go too fast, where you couldn't do that, I suppose, even though I'd rather see all of your lovely faces. You can pause. You can't pause me in the classroom, but you can pause on the computer. I ended up having to do that last night. I watched a video, and it was nice to be able to push pause so I could catch up and then go back. So I did say that, again, with special rights that are right isosceles, you have options, the Pythagorean theorem or this pattern. This pattern is huge. It will make things go a lot faster. So one of, real quick before we're done, because we're going to be done for the day in a moment, I've never actually taught this lesson this way. Typically, I would simply say copy the formula, and then every one of the problems, we would just use special rights. So the last example I'm going to put up here. All right, because you are, of course, going to have a couple questions at the end of your next no reassignment that are going to have you need to slow down. Slow down, read it, and realize that all of them are pretty much the examples that we just did. So as I jibber jabber here a little bit, make sure you copy this down if you're working with me. I will tell you that I will update everything in the gradebook between today and tomorrow. You will find things updated already in NoRe, and you will find that your next assignment has already been handed out, and that will be, like I said, I've already done probably 1, 2, 3, 4, 5, what will be total, you'll be able to answer right now 7 questions without a whole bunch of effort because I just answered them all in the notes. So you will find all of that updated in Google Classroom. All right, so a couple big things in this. Please pay attention that we do say square, which immediately means all the sides are the same and we've got right angles everywhere, because a square is both a rhombus and a rectangle. We've got our right angles, we've got our congruent sides. We also know that all of our angles have been bisected by the diagonals and all of them are congruent. So right away, because of just the vocabulary, we know that we have 45, 45, 90 triangles everywhere. We also know that the diagonal is 24 inches long, so we're going to throw in the 24 inches here. Bigger question, though, is we don't just care about what the legs are, we care about the whole perimeter and the whole area. So slow down and make sure that you are answering the questions that are being asked, not just a question. We know there's always multiple steps here. Again, I'm going to approach this from both methods. So you could go about this with our Pythagorean theorem. Again, with our x, and then our 24. So we have x squared plus x squared equals 24 squared. So 2x squared equals 576. Double checking. I should trust my gut. And we are going to go ahead and divide by 2. And we end up with x squared equals 288. Well, thankfully, we've already seen that before. So we know that when we take the square root of 288 is 12 radical 2. Now we do end up with a radical 2. It just so happens to be on the legs this time, so do not get confused. We have a whole number on the hypotenuse. Notice where that radical 2 now shows up. So we now know that each of these sides are going to end up being 12 radical 2. And it's not a coincidence that 12 is half of 24 and that the radical 2 shows up here. It'll happen every time. Now I could do this using our special rights and our 45, 45, 90 pattern. And so I could do this using that AA and A radical 2 formula, where we know that because they are next to each other, they are going to be set equal. So A radical 2 will equal 24. And we are going to divide by radical 2. And when we divide by radical 2, you cannot leave the radical in the denominator. That is not allowed. You need to do, so this is no, not appropriate as a final answer mathematically. Okay, we need to do what's called rationalize. And we did this way at the beginning of the year. We talked about how to rationalize. And when we rationalize, we want to multiply top and bottom by a special number 1. And it's going to be whatever makes that radical a perfect square. Well, 2 times 2 is 4. So we're going to multiply radical 2 over radical 2. Notice that's 1. So it's going to look different, but the value will remain the same because anything times 1 is still going to be itself. So what we end up with now is 24 radical 2 over the square root of 4. And we know that the square root of 4 is 2. And 24 divided by 2 is 12 radical 2. Now this pattern is again something that we talked about at the beginning of the year, where some of us may be able to jump from here to there very quickly because we know that we just yanked that radical to the top, and what was inside, the radicand is what it's called, stays at the bottom. So some of us will be able to make that jump and then do the division. So this part might seem lengthy, but if you see that pattern, it will go fast. Now, we're not done. We figured out how to find the length of the side, and we know that each side is going to be 12 radical 2. And I'm going to put a big old or between here because you don't have to do both. It's whatever seems to be faster for you at the time. But now what we have to do is we have to figure out how do I get back to solving for perimeter and area. So we're going to shift this up a bit. We're going to draw our A, B, C, D again. And now we found out that even though our diagonal was 24, we just found that every one of these sides is 12 radical 2. So if we want to find perimeter, we're going to take that 12 radical 2 plus 12 radical 2 plus, or you could have done times 4. Doesn't really matter. A lot of people like to associate perimeter with adding. So 4 times 12 radical 2. We only have to worry about those numbers that are the same. So the radical 2 acts like our variable. And we find out that this is 48 radical 2. So our perimeter is 48 radical 2. Then when we do area, we have to remember that this is a square. So you could do base times height, you could do side squared, doesn't matter, it's the same thing. And now we have 12 radical 2 times 12 radical 2. Well, 12 times 12 is 144. Radical 2 times radical 2 is going to be the square root of 4. Well, the square root of 4 is 2. So we find that our area is 288. So keep in mind that it's not just, and I will tell you that the bulk of your no-read questions are going to be find the side, find the side, find the side, find the side. It's a lot of the questions are that. I think the last two have you looking at a shape that isn't just a right triangle. So Pythagorean theorem will bail you out, but I do suggest really working on recognizing your special right pattern, that 1 to 1 to radical 2, that A radical 2 pattern. Before I sign off, are there any questions that you guys have for me? All right, if not, please check Google Classroom. I will upload these notes here within the next hour or so, and you should have everything there that you need. Continue to check not just Google Classroom, but email me if you have any issues with when you check PowerSchool. Again, I should have most everything you have just recently turned in over the last couple days updated here within a day or so. So I appreciate you guys who join me so that I feel like I'm talking to somebody. Hopefully your counterparts are watching the videos later. And again, if you have any questions, just toss me an email and I will talk to you again on Wednesday. Check Google Classroom. Thanks, guys.